When you try to change a piece of software, the representation you choose dictates the speed of the edit. In comparative studies, researchers found that executing the same conceptual change in a graphical interface took roughly 10 times longer than doing it in text. This metric comes from the cognitive dimensions research of Green and Petre. They weren't interested in the code versus no-code culture war. They were measuring the objective speed of modification across different environments. That 10x time disparity is an architectural verdict. It tells you whether your workflow representation makes future iteration a routine update or a significant project expense. I'm Bearded AI Guy, analyzing the technical framework of the human architect, author of AI Agents in Action. We're asking a specific question. Does code actually outperform nodes for open-ended agentic workloads? The answer depends on whether your architecture makes the cost of change computationally and cognitively cheap or prohibitively expensive. To understand that cost, we have to look past the UI. The binary between code and no code is an illusion, as AnyDen's own documentation makes clear. Every visual workflow you build is saved as a serialized JSON text file and managed in Git-backed environments. The visual canvas isn't a different category of program. It is a restricted, often high-friction interface overlaid on top of a standard text-based program. This is why professional change reviews in these systems still happen as JSON diffs. Text remains the underlying source of truth. The real question isn't whether to use code, it's which interface to the program makes altering its logic most efficient. We can use Green and Petre's cognitive dimensions of notation as a framework to measure this efficiency. It provides an empirical way to evaluate the friction within any software environment. First is viscosity. Pulling one node makes the entire web fight back. Next, visibility. Graphs sprawl, making comparing two distant parts impossible. Finally, diffuseness. The real estate cost where a dozen graphical entities express what fits in 2 lines of text. These 3 dimensions explain why complex visual graphs eventually feel like wearing a heavy sweater that physically resists you when you try to move. Using a raw LLM API is like renting a power tool. Using an agent SDK like Claude Code is like owning the entire workshop. The SDK exposes a text-native environment, where operations like read, write, edit, and bash are first-class tools. Because session memories and tool uses are serialized locally as plain babst, the entire architectural stack remains uniform. This uniformity allows mature engineering operations, like global search, diffing, and refactoring across your entire automation. By staying text-native, you remove the black box of visual platforms, governing your AI agents with the same rigor used for any other mission-critical software. To see the difference in practice, consider a standard email triage workflow, handling drafts, schedules, and tickets, built in both a node graph and a Python file. For the initial first draft of the logic, both representations work well. They both handle the basic, predictable flow. But business logic is rarely static. Suppose a new policy arrives. Treat a specific sender as a low-priority newsletter unless the CEO is included on the thread. In the visual graph, adding this exception means severing connectors, building new branches, and rebuilding spatial topology. In the code version, you simply add one new sentence to a prompt. One is a structural rebuild, the other a simple edit. This is the abstraction collapse. Visual systems force you to translate semantic policy changes into complex spatial geometry, which makes scaling nearly impossible. This doesn't mean visual tools have no place. Platforms like LabVIEW have thrived for decades, and Scratch is a proven on-ramp for education. LabVIEW succeeds because the domain of hardware testing is naturally signal flow shaped. The visual representation matches the physical reality of the engineer's bench. Visual tools win when the transformations are bounded and the primary barrier is learning syntax. But modern AI automation isn't bounded or spatial. It relies on open-ended reasoning and evolving text policies. Using a node graph for complex AI logic forces a spatial model onto a non-spatial problem. Friction is the inevitable result. Ultimately, visual tools and code are optimizing for different outcomes. Visual environments optimize for onboarding, inspection, and the speed of building your very first prototype. Code optimizes for semantic compression, modularity, and infinite changeability. It is built for the long-term maintenance of complex systems. Once a workflow moves past being a simple pipeline and becomes an AI reasoning system with dozens of exceptions, visual optimizations lose their utility. In production-scale agentic automation, the ability to iterate quickly and manage complexity makes code the more effective architectural choice. A complex visual workflow is often just code burdened with a less efficient abstraction. Tell me in the comments about a workflow you've stopped updating because the effort to change the nodes became too high. For the full research and cognitive studies behind these findings, look into AI agents in action. On day 4, we'll look at the specific cost ceiling teams hit when they try to scale platforms like N8N and Zapier. For general-purpose AI automation, text-Maeve workflows provide the efficiency needed to keep iterating long after the initial demo.